Hi, everybody. I got back just in time for the song to fade out. Just a second. Hi, someone's here. Do you want to say hi? Say hi. I don't know if you can hear her. But as soon as I started talking, Maya wanted to say hi to everybody. Hi, welcome back to Chem 163. Oh, it's Wednesday. And the second I announced on Monday that lab was back on, I immediately got an email from the lab coordinator who said, yeah, the NMR broke again. In a different way this time. I'm like, oh, great. Your timing couldn't have been worse. So I sent out an announcement yesterday. Hopefully you got that email. But there is no lab this week. I particularly like lab number 3 because you get to play with all this really cool instrumentation that's important for science. So odds are, what I am currently thinking is that so there's no lab this week, regardless of what I'm going to say here. But what will probably happen is that we're still going to do lab 3. We're not going to just skip it. We're going to skip some other lab that I think is dumb. Like, whichever one the KSP lab is, it's calcium iodate. I think that's 5. That'd be my first choice to get rid of and still do number 3. So, I will update the schedule later this week because I still have a lot of stuff to do. And let you know which labs we're going to be doing when. But of course, this is all contingent on the NMR being fixed reasonably quickly. And with $250,000 instruments, quickly is not a thing that happens. So I really don't know when it's going to be fixed. So it may be a moment before I can update the schedule. So please bear with me and our NMR. Let's see here. Lab worksheet number 2 is still due this Friday. You do not need to be on campus, obviously. I closed the pre-lab number 3, so that no longer exists on Canvas, so you don't have to do that yet. I don't think anybody did do it yet, but if you did, it'll just sit there for now, which is fine. And there's an exam next week, so we need to go through more of the material from Chapter 14. And I need to put a quiz online, which I'm going to try and do tonight. I'm going to try and grade your quizzes and write a quiz for Chapter 14 so that you at least see some questions that might show up on the exam, because we're not going to finish Chapter 14 before the exam, I'm realizing. It's just so long. All right. The other day we were talking about how to calculate the pH of a weak acid and a strong acid. So we did a bunch of those calculations. Today what we're going to do is we're going to do mixtures of acids. So if I give you multiple acids at once, what do? And you might think, well, I'll just add the H3O pluses together. And you're absolutely right. But what we're going to find is that in like 90% of cases, adding the H3O pluses together is going to fall out of the range of sig figs anyway. And so you could just save yourself a bunch of time by just considering one acid, and that's the stronger of the 2 acids. So when we are looking at mixtures, here's what we'll do. Only consider one acid. And in fact, we've been doing that all along. Because when we were considering weak acids, there was another acid in the water. It was water itself, the autoionization of water. And we just sort of ignored that, right? Because 1 times 10 to the minus 7 moles per liter of H3O plus not going to affect our times 10 to the minus 2 amount of whatever acid we're working with, right? So this is not really a new topic that we're only going to consider the acid that contributes the most in a solution when you consider the autoionization of water. Let's consider these 2 acids mixed together. So I have a strong acid. I have 0.1 molar HCl and 0.1 molar formic acid, which is a weak acid. Where are all the places that H3O plus comes from? I've listed them all here. So the first one, here's my H3O plus and here's Ka for that acid. It's a strong acid, so essentially all the HCl that you put in there becomes H3O plus. Then I have my weak acid here, and it has a much smaller Ka, so much less than 0.1 molar is going to dissociate. And then I have the autoionization of water here, and I've written Ka, but technically this is Kw. Now, if we're going to do this calculation and figure out how much H3O plus happens here, when I type in my number for my negative log here, so I'm going to do 0.10. I'm going to log negative that. Oops. Uh-oh. Oh, I tried to natural log a negative number. That's what I did. That's what I want. So 0.10 log, and then this. There you go. So that's the pH of that. Let's suppose that I added in just the autoionization of water, though. So that would be 0.1, 2, 3, 4, 5, 6, 7. And then I'm going to log that. How much does that affect our end result? Contributing the autoionization of water. You'll notice that we've changed the result some 6 decimal places down, right? But as far as sig figs are concerned, these are the only 2 numbers that we care about. So water didn't contribute anything to our result. And this is just how natural log works. Natural log operates on, or not natural log, I'm sorry, base 10 log operates on powers of 10. Every time you increase the order of magnitude, you move over a decimal place. Or you move up a number in log. And so if you have a really, really tiny change of something before you log it, it's going to end up way buried in these decimals that change. Now, what would the contribution for formic acid here be? If I had to guess, I would say it'd be something like this. So there's our, oh goodness, 0.1. Let's say something like this. That 0.0003 would be from our formic acid. And even if I hit log on that, like not much of a difference, right? So we really only have to consider the strongest acid here. Because when we do sig figs, it's not going to matter anyway. You'll notice that all of our KAs only have 2 sig figs. So our answers are going to end up with 2 sig figs in them. And our pHs are going to end up with 2 decimal points. And it's just not going to matter. All right. So I actually did do this calculation. I got times 10 to the minus 4. I wrote in a 3, which was even bigger. We've done enough of these calculations, so I'm not going to actually show this calculation on the board. And there you go. Now, the thing that you'll notice is weird about this is this number right here. Why is H3O plus from H2O only 1 times 10 to the minus 13? And the answer is, it's Le Chatelier's principle. How the heck does Le Chatelier's principle work here? And the answer is, well, if I add a bunch of acid from the HCl, that's going to affect equilibrium too. I think that's a much more interesting problem. So, how do we deal with that, actually? And the answer is, well, whatever the initial conditions are, we're just going to add those to our ice table. So these are both water, so we don't care about them. But initially, we would put something like this here, right? Except in this case, because I have the HCl that I've added, well, actually what I should do is I should do this. It's something like that. And then water is going to dissociate. And this will happen. And so Kw would be something like that. And then I have to go to Wolfram Alpha and solve this equation because it's a quadratic and I don't want to deal with that. So you are allowed to enter numbers other than 0 for the initial part. Wow, Wolfram Alpha is taking its sweet time to load today. Oh, not 10 to the positive 14. So 1 times 10 to the minus 14 equals 0.1 plus x times x. And when we solve this, oh, I didn't put it on the screen here. Sorry, hold on. You'll notice that the value that we get for x is... Oh, right, it plots a graph here. I got to scroll all the way down there. So x would be negative 0.1. That's not possible, obviously, right? Because otherwise I would be losing acid. Or 1 times 10 to the minus 13. And so what ends up happening here is, I'm going to clear this real quick, but we'll write down what our result is. Is that because I put a number up here that wasn't 0, I got a different number down here that I would have expected, because this number changes everything, yeah? And that's Le Chatelier's principle in action. If I add extra acid, I'm going to drive equilibrium back in this direction, relative to what it would have been if this was a 0. Because if this was 0, and I got rid of this number, then this would have been this, right? Because I would have had x squared equals 10 to the minus 14. But because I have that extra thing in there, I change the equilibrium and it will settle to some different number. So entering in numbers here will affect your end result. And when you have mixtures of things, it's important to remember that, yeah, I'm not always going to have zeros initially. Okay? I can still solve the equation. Anyway, that's where that number came from, in case you were curious. I can do the same thing for the HCHO2 equation, where I also say the initial amount of H3O plus is 0.1 molar, and that's how you get this number. And you could try that as an exercise for yourself. But this one is probably the weirder of the two to look at and be like, huh? I thought it was times 10 to the minus 14, which would make it 10 to the minus 7, right? But the point is that when you add all of these numbers together, this is really tiny and doesn't actually affect a decimal place we can see. And this is like stupid small. Who gives a shit, right? So this is the only number that we're going to care about for pH. So there's your takeaway. If you mix acids together, use the strongest of the acids. If it's a strong acid, that's the one you care about. Now, what happens if you have 2 weak acids? Well, it's the same issue. Which of them is stronger? Which one do you care about? Now, the answer here is that if your Ka values are different by at least 100, so a factor of 100 is what you're looking for. Look for a difference in the exponents of 2 or more. If that's the case, then the stronger of the 2 acids is going to be the one you care about the most, and you could just ignore the others. Otherwise, you have to do this nonsense where we had to add in this number. We would have to do a calculation, get a result for X for the strongest acid, put that number in for the weaker acid as the initial amount and see what happens, and then sum them both together, and then just keep doing this iterative equation over and over and over again. But we don't want to do that. We want to simplify. So if we have an acid with a Ka that is 100 times bigger than the other one, we'll just use that one. Now, there is another catch to this. The stronger acid has to be the more concentrated one, or both of the acids have to have similar concentrations within about a factor of 10. If you have a very, very dilute stronger acid and a very concentrated weaker acid, then this doesn't work. So the first thing you want to do is look at the concentrations, and if they're you go, oh, they're mostly the same. For example, on this one right here, here are my concentrations. I got 0.125, 0.009, or sorry, 0.0900. Those are roughly 0.1, right? So they're about the same. So that one checks out. And then looking at my Kas, I have a 10 to the minus 4 and a 10 to the minus 8. So what that tells me is, okay, my acids are both the same concentration, more or less, and also one is 100 times or more stronger than the other. So what I'm going to do is I'm going to say, okay, I only care about the stronger of the two acids, and that's going to be these. The other two I can just ignore. So now that we've ignored one of the acids, this is just a weak acid problem. And I did tons of these on Monday, so you get to do this one. What's the pH of a mixture of 0.125 molar HF and 0.09 molar HClO? Here's their Kas. Hey, the HClO is the weaker one, you could just ignore it. So tell me what the pH is. I'll give you about 5 minutes, and we'll go over the answer together. All right, 1 more minute, we'll go over the answer. All right, so let's go over here where you can't see the problem because it fell off the screen. All right, so hopefully we've done a few of these in the homework exercises on the textbook. So I'm going to operate on the, first of all, let's cross out water because nobody cares, it's a liquid. I'm going to operate on the assumption that HF is really the only acid that's in there because whatever number I enter here from HClO, it's going to be real small. So let's do this. This is how much I start with. I essentially have nothing in here. I definitely have none of this. I'm going to allow the reaction to go, so I'm going to use up this. I'm going to create that and that. And so there's my totals at equilibrium. And so that's going to equal Ka is going to equal H3O plus times F minus divided by HF. And that's going to be, so that we got X and X, which is X squared. And then I've got HF, which is 0.125 minus X. And this is going to equal our Ka, which we said was 3.5 times 10 to the minus 4. We could just throw it in Wolfram alpha, or we can say, okay, X is small. Gotta check it afterward if we do that, but don't worry, X is small. I mean, I hope it's small. And so that means that after we've done our algebra here, this 0.125 will come over here. This X squared will be square rooted. I just noticed that I use both a times symbol and a dot. And now I feel kind of dirty. Anyway. That's not how I meant to do this, but that's okay. Ooh, -4. Ooh, I almost screwed that up. Okay, so there's our number. We're going to square root that. 0.0066 is what we get. And so remember that this is equal to H3O plus. So we'll pH this. Again, pH is minus log base 10 of H3O plus, which is minus log 10 of that number that we just got, which looks like it's going to be around 2.5, we'll say. So log that. Oh, I was close. So that would be the pH of this solution. Now we could look at the contribution for HClO. We could do that equation, see how much H plus it contributes. But what you would discover is it would be so much that it would barely change the pH. If it went down to 2.17, I'd actually be surprised. All right, we got 2.18. My answer actually has 2.20. That's good enough for government work. All right, so mixtures of acids are actually just pH calculations for one acid. Just consider the most concentrated acid. All right, I'm going to leave this problem for you to try on your own. You'll notice that, hey, these are similar concentrations, so that works. You'll notice that the Kas are sufficiently separate. So you could figure out the pH of that, no problem by yourself. So we're going to move on to the next topic. If you have any questions, let me know. All right. Now, you might have asked yourself, just out of a curiosity, this is a question that actually comes up from various students. When they see pH, you might wonder, what the heck is P? And it turns out P is a function. P is this. You just take the log base 10 of some number and then you negate it. You can do that to anything. And the reason that we do this is to take numbers that are on a range of like 10 to the minus 10 all the way up to 10 to the positive 10 or whatever, and compress them down into more reasonable numbers. So the pH scale is just taking the negative log of the concentration of H. What do you think the pKa scale would be? It'd be taking the negative log of Ka. So let's just take some acids here. So I'm just creating random Kas here. And what I should have done is given this more space. If I want to find the pKa of this, we'll just type our Ka in the calculator. And then we'll log it, and then we'll negate it. So the pKa of this number would be 3.74. The pKa of this number would be like 7 something. Yeah, there you go. And so what we can see is that the pKa scale is just another scale, and really what it is more or less the exponent, right? Because this is almost 4, this is almost 8. It's somewhere in the middle because our numbers are somewhere in the middle. And so we can see that the one with the 10 to the minus 4 is the stronger acid because it has a higher Ka, right? So the lower pKa is, the stronger the acid. Just like pH, right? The lower the pH is, the stronger the acid is. Same is true with pKa. So if something has a pKa of, like, say, 1, that's going to be a real strong acid. Something has a pKa of 50, that's going to be extremely weak acid. Now, when do pKa's come up? Well, if you're taking organic chemistry, they come up all the frickin' time. So, organic chemists love pKa's. We're going to use pKa's later on in chapter 14 for a very specific purpose. It's going to make our calculation life so much easier. But it's important to know what a pKa is. Oops, okay. We'll come back to that later. That's it for acids. Are you ready to do everything again with bases? And if you're saying, no, I'm fucking not. I hate it. I hate the calculations. There's so many. Then that's normal. But also too bad, I guess. This is what you signed up for. Welcome to Chem 163, question mark. Now, because we've done these calculations already with acids, this should be pretty straightforward. But when we're working with bases, we do have to remember that our equation is going to look very slightly different. For one, a base creates OH minus, right? So we're not going to have H3O plus in our equations at all. What we're going to end up having is OH minus. So at the end, we're going to solve for the POH, which we can turn into a pH. All right. So let's do some exercises with strong and weak bases. Remember that strong means total dissociation. A strong base would do something like this. And if I had to write an equilibrium constant for this, which it's a base, so I'm going to call it Kb. I know, real novel, right? Kb for this would be infinity. Because it's a strong base, right? Same for strong acids. Now, any hydroxide containing alkali salt, so lithium, sodium, potassium, including rubidium and cesium hydroxides, I believe, too. Those are just less common. As well as some alkali earth metals, so strontium, calcium, and barium. Really, the big ones are magnesium and beryllium. Those are not strong bases because they are insoluble. But more or less, if you're in group 1 or 2 and you're a hydroxide-containing base, you're a strong base. And these are the only strong bases. So figure 14.6 in your textbook. I don't know what page that's on because it's a web URL. But it is in the section 14. I believe it's 14.4. Let me see what that section is. No, it's 14.3. Okay. So figure 14.6 and 14.3 has the list of strong bases. And again, yeah, we don't care about magnesium and beryllium because they're insoluble, essentially. Something that's important to note, I would have totally forgotten about this if this didn't just pop up, is that some bases produce 2 hydroxide. And so if those are used, be careful, because your balanced chemical equation is going to have a 2 in it, which means that your ice table is going to have a 2x in it, and when you do stoichiometry, it's going to have a 2, and using calcium hydroxide and strontium hydroxide and barium hydroxide as titrants is basically like, oh, the instructor is in a bad mood today and wants us to suffer. I say that because Steve does. And Steve, it's not that Steve is in a bad mood. It's that Steve is just a giant asshole when it comes to some of these problems. And that makes me laugh. So now I feel obligated to also do this sort of thing. So be mindful. If you get a titration problem, look at your base. Don't assume it's sodium hydroxide. Double check to make sure that you aren't getting 2 equivalents. Because if I give you one with 2 equivalents and all your answers are off by a factor of 2, that's going to suck when you get your test back and it's like just red ink all over it. Like, you forgot the 2. We don't want that. All right. Remember that a base takes H+, and the source that it's going to take it from is H2O. And that's going to look like this. So whatever our base is will react with water to form BH+ and hydroxide. And if we're going to write our equilibrium expression for that, well, again, we don't care about water. It's a liquid. Kb would be BH+, hydroxide, and then the base. And then we would solve this in exactly the same way as a weak acid. You're going to have a bunch of x's on the top. You're going to have some number minus x on the bottom. Use x as small. The end thing that is going to happen is that when you solve for x equals whatever, it's not H3O+. You're getting hydroxide now. And so then the next step would be to say, oh, okay, well, I need to calculate the POH and then turn that into a pH. So that's your blueprint for attacking weak base problems. It is otherwise exactly the same math, so we're going to try and speed through a few of these. So again, there's Kb. Now, do I say Ka times Kb equals Kw here? I don't. I don't know where I say this, but I'm going to mention it now just in case I forget. Let's go over here. So there's an interesting thing that comes up about Ka and Kb, and that is that Ka tends to be the number that everybody records in tables, but Kb is not the number that is often found. And I believe we're going to talk about this later, but if Ka equals something like this, for a conjugate acid-base pair. So the conjugate acid-base pair for this would be, so this would be like B. And so this would be for this reaction. Let me just write out the whole thing here real quick. And this would be for oops, not 3. So if I had this reaction, I had the acid part of this acting as an acid, I would write that as my equilibrium expression on the top there. And then for the base, we just saw that on the PowerPoint here, right? So what I can actually do is if I take these two things together, I'm going to say, what is Ka times Kb? And so what I'm going to get is so here's Ka. And then here's Kb. You're going to notice something real quick here. Oh, these cancel, and so do these. And what do you get when you're done? Gee, this looks familiar, doesn't it? So, we have shown that Ka times Kb equals Kw. So, if you are missing Kb, if you cannot find Kb somewhere for a given acid-base conjugate pair, you can calculate it. So, now the caveat here is that these are the Ka and Kb values for conjugates. So, an example would be, if I know Kb for ammonia, then I would know Ka for ammonium. And vice versa. If I know the Ka for, say, acetic acid, I could calculate Kb for acetate. So make sure you're selecting conjugates. And if you're doing a reaction and you're like, hey, I recognize that, that's a conjugate of something, I'll go look up its Ka or Kb. And so you could go look up the Ka or Kb of the other common thing, calculate the Ka or Kb for the less common thing by using the formula up there, Ka times Kb equals Kw. Okay, so that's just my way of saying you may not find a Kb for every number. And if you can't find it, this is how you get it. I don't know where this is going to come up in the slides, but I was thinking about it, so I thought, we might as well just mention it. All right. Now, how do bases actually work, like, in terms of their structure? So, this right here is the structure of ammonia. I'm going to just write the nitrogen over where the blue orbs are. These are H's. And then all these black spheres are carbon. Now, a feature about nitrogen in organic chemistry, although ammonia is not organic, but that's okay, is that it tends to form 3 bonds, and then the last site in its geometry, we would say, is a non-bonding pair. Well, non-bonding pairs are not inert, it turns out. Non-bonding pairs will react to things that have no electrons to form a bond. And so when ammonia interacts with H+ to become ammonium, it will form this bond as shown. So it's the lone pair on nitrogens that is the attractive force for the hydrogen ion. And it turns out that in virtually every type of arrangement that you have a nitrogen that has just an extra pair of electrons on it, it will do this. Now, its ability to do this goes varying degrees based on what is bonded around it. So, for example, ammonia is a better base than methylamine, which is a better base than pyridine, I believe. I don't know their Kb values off the top of my head, but the more stuff that you have bonded to a molecule, the more crazy changes occur. And it's not universal. It's not just more bonds equals weaker base or something like that. It totally depends on the structure. And I could talk about that for hours because that would also involve my research as a graduate student. Not necessarily acids and bases, but how bonding affects electron density around what we'll call the active site, which in this case is the yellow balloon, for the either sp3 orbital or the sp2 orbitals that we're drawing. So let's not get into that. The important thing is that the electron pair is where H is attached to. All right, let's do an example. What is the OH concentration and pH of this strong base? Well, that's not difficult to do, right? It's a strong base, so we know how to figure out the POH and then the pH of it. So KOH, oh, we're writing in red now. I guess we'll just do this. This isn't really going to do anything how I want to write it, is it? Okay. Because I'm just going to get the water back when I write it that way. So there's no equilibrium expression to really worry about here, because it just dissociates completely, because it's a strong base. And so that would be minus log. Oh, there's a cat right here. Hi, I'm doing chemistry. So here's our POH. So 0.265. We're going to log that. So that equals 0.577. And then we also know that POH and pH added together equal 14, right? So therefore the pH must be 14 minus this number. So we're going to make it negative, and we're going to add 14 to it. 13.423. So there you go. That would be the pH of a strong base, which is very straightforward. We can do that. All right. Now let's do the same thing again, but you'll notice that I'm being a jerk this time. So I want the concentration of hydroxide and the pH of this solution. So I'm going to give you like 2 or 3 minutes to calculate that on your own. Again, note the 2. And then we'll go over the answer in just a bit. And then I think we're due for a break at that point. All right, one more minute. We'll go over the answers. All right, let's go over the answers. But first, I have to get this cat off my lap. Here you go, Kresnik. Go in your bed. You're going to your bed. It's right here. I put it on the couch for you. Here. Go in your bed. He's going to try and jump right back on my lap, isn't he? Yeah, he is. Okay, well, I'm going to lean forward so that so there's no space. The joy of cats. Hi, you're a cat. Yes, I see you. All right, so for this problem, we have strontium hydroxide. And so that dissociates into 2 hydroxide. So that means that the amount of hydroxide that's in solution will be 2 times the initial concentration. Because this is the initial concentration, right? So then the pOH of this would be that, which is minus log of 0.0056. And I don't know what number that is off the top of my head. That's like 3 something, right? So log negate equals 2.25. And then pH plus pOH equals 14, of which we know this number. So, Dut plus 14. So that's what I got, 11.75. All right. So double check your math. And oops, we'll see what we got over here. Boop. Yeah, that's what matches what I got. All right. So when we come back, we're going to start doing some equilibrium expressions using weak bases, and it's going to be the same thing that we did on Monday with our ice tables. So we'll see that in just a little bit, but we'll put this on the screen for now. Oh, I need my clock. So why does the clock always appear over there? All right. Do you want to update the clock? No, never update anything. Right? All right. So we'll start this, and we'll see you in 10 minutes. Alright, we're back. Let me wind this down real quick. And then, let's see if we can, get a sound out of Maya. Hey, Maya. Say hi. Maya. Hello. There we go. Hopefully you heard her. Maya's here now. Actually, they're both in here, so I might get interrupted by cats. Alright, let's see here. So, what we're going to do now is we're going to just play with weak bases. So, I'm going to give you an ammonia solution. And I've given you Kb for ammonia because that one's actually well known. And I want to figure out what hydroxide concentration we have and its pH. So, we're going to get this as just part of the problem. So, this is not going to be a huge out-of-the-way thing to do. So, I'm going to do one, and then you're going to do a bunch of them. So, let's get our equation for ammonia set up. So, ammonia will react with water. And it will become ammonium. And, oops, hold on. Sorry, I forgot that. And it will create hydroxide in the process. So we're going to make an ice table. And again, water, nobody cares, right? All right, how much ammonium is there in the beginning? Well, there's none. How much hydroxide is there? Well, there's essentially none. And then, just like before, okay, I'm going to use up some of my reactants. I'm going to create products. So at equilibrium, this is what I have. And then now I can write the Kb expression. It's a base, so it's Kb. That's going to equal ammonium, hydroxide, and ammonia. So that will be this. And that's going to equal Kb, which is 1.76 times 10 to the minus 5. Guess what? We're going to do this. X is small. I just realized that in the previous problem we never checked it. Don't worry, it was small. And so that means that I'm going to move the 0.2 over. I'm going to square root. X will equal square root 0.2 times 1.76 times 10 to the minus 5. And we'll actually check this one because I forgot to check it last time. Times 10 to the 5 negative. So there's our inside the square root. There's our outside the square root. And you can see that this 0.1, we're not going to check it. I was just kidding. This 0.1 coming from this point, or sorry, this 0.001 from this 0.2, this is 0.5%. Like if that was a 2, it'd be 1%. So we're going to assume that that's fine. And it is, don't worry. So if X equals hydroxide, then this is the amount of hydroxide in the solution. 0.00188 moles per liter. And you can POH that, of course. At this point, I'm going to assume that you know how to POH something and how to pH something. So I'm going to log a negative 727. And then thus the pH would be 14 minus that, which is 11.273. There you go. At some point, these calculations become old hat. And really the trick is going to be just learning all the nuances between what I do for an acid, what I do for a base, what I do for a mixture of acids. What happens when I put an acid and a base together? That's the end of this chapter. So we will do that. Don't worry. All right, so there's the answer that we got. Hey, that matches almost exactly. Good job, us. We're so good at chemistry. All right, here's one for you. I'm going to give you methylamine. 0.30 molar methylamine. Here's its KB. Tell me hydroxide and the pH. So do everything I just did. You can rewind the video if you need to see my example and just follow along with it. But it should be the same calculations that you're used to. So I'll give you 5 minutes, and we'll check in after that. All right, one more minute. We'll go over the answers soon. All right, so, oops, hold on. There we go. All right, so we got our ice table set up here. And so our initial amount of methylamine, we're going to put this. Water, nobody cares. Goodbye, water. How much methylammonium is in there at the start? Well, I certainly didn't put any in there, did you? No. How much hydroxide is in there? Whatever water contributes. Nobody cares, right? So, there's our initial concentrations. We're going to let the reactants react, and we're going to produce products. And then we'll just tally the results. So, there's how much I'd have at equilibrium. I'd have this much and this much at equilibrium. It's a base. So we got the products over reactants. And that's going to equal x squared over 0.30 minus x. And that will equal whatever the number is that I gave you. All right, so don't want to deal with the quadratic. We'll just get rid of this. That simplifies our calculations. So now x is going to be square root 0.30 times kb. And that ends up being, who knows, right? 4.4 times 10 to the minus 4 times 0.30. And then we'll square root that. And, oh, wrong end of the pen. 0.011. I only get how many? 2 sig figs? Yeah. 0.011 molar. So that's X, and we know that X is actually hydroxide. So there you go. So there's your hydroxide concentration. And then you can POH this. So we're going to go log negative. And then we can pH that. And that's going to be 14 minus that number. You'll notice that I'm making it negative and then adding 14 to it. That's just because I don't want to type in 14 minus whatever number was in there already. Just trying to save time. Like, why does your calculator say negate, negate? Why just not negate? Because we need the answer before we do that. I just poked the cat with a pen. He was not very happy. Sorry, Kresnik. He's trying to sit in his bed, and I just poked him with the pen, and he's like, where did that come from? Now he's just staring at me. I gotta click over there. There we go. All right. Oh, hey, here we go. Ka, Kb, Kw. We already did this, so there's our math. Hooray. We already knew this. I didn't know where this slide was, and I was too lazy to look for it. But we already talked about K times Kb equals Kw. You can look at that in the earlier hour of this video. And again, this is useful if you don't have the right Kb, because not all bases are listed in the Kb table, but a lot of the acids are. So if you have the conjugate base of an acid, you can easily calculate its Kb. Oh, look, it's the exact problem that I had mentioned before. It's like I'm clairvoyant. I always end up doing this. So, okay. I want to figure out Kb for acetate here because I don't know what it is. It's not in a table. It's probably in a table, don't worry. So, what we can say is, okay, well, Ka times Kb is Kw. So that means that Kb must be Kw over Ka, which would be this over the Ka that we were given. And so we could type that in the calculator. So 1 times 10 to the minus 14 divided by 1.8 times 10 to the minus 5. Boop. So, no problem. We can do that easily. All right. So, I'm going to have you do one here. I have a Kb value for carbonate. What is the Ka value for its conjugate acid? Well, first of all, what is its conjugate acid? I'll give you a hint. It is not this. This is not its conjugate acid. That is an acid, but it's not the conjugate acid of carbonate. So, I want you to tell me the Ka for the conjugate acid and also what the conjugate acid is in the chat. So, I'll give you... This is 2 minutes to do this, so I'll give you 2 minutes. We'll check in and then. All right, so you have the right conjugate. Very good. So remember, conjugates differ by H+, so the conjugate acid would be this. Now, it turns out that bicarbonate is still pretty basic. The pH of a solution of bicarbonate is like 8 or so, so it's very weakly basic. It's almost neutral. So if I want to figure out the Ka value for this, what we would do is we would say, okay, well, Ka is Kw. That's not Kw. Kb. Which would be 1 times 10 to the minus 14 over Kb, which is the number that is given. And that's going to be like 10 to the minus 9 or something, right? So 1 times 10 to the minus 14 over 2.1 times 10 to the negative 4. I went the wrong direction. That's okay. 4 point... How many sig figs? 2. Oh, my pen screwed up there. All right, so there would be Ka. So, in other words, not acidic at all. Well, 10 to the minus 11, but you have the right idea. All right. And that appeared over my text. Of course it did. Let's go. Boop. There we go. All right. So that's really all the calculations we're going to do for Ka and Kb in this section, at least. Let's talk about some features of strong acids. So this next part is a structural analysis, in other words, of like what makes a strong acid be strong. So I've sort of just listed a bunch of strong acids for you, but what are some features that we care about that make acids stronger? And so those features are the following. The bond between the hydrogen and whatever other atom is there tends to be really polar. Now, as a result of that, the bonds end up being weaker due to the fact that the electron density is being pulled towards the electronegative thing, which makes it tend towards ionic. Since an acid is mostly just an ionic bond between H plus and the rest of the molecule, in other words, if it falls off anyway, then the more it looks like an ionic compound, the more likely the H plus is just going to pop off as an ionic compound because it would get hydrated. It's the covalent character of the bond that holds the H there in the first place. So with acids, the bond tends to be extremely polar covalent. It is on the verge of breaking. Now, the way that we can look at this is we can look at electronegativity. Remember electronegativity from 161? That was so long ago. So, the electronegativity of H, so we'll write that down here. Electronegativity. H is 2.1. I know carbon is 2.5. And I know fluorine is 4.0. I don't know what lithium is. I'm going to guess 0.9. It's less than hydrogen. I know that for sure. So, if I put in all the hydrogen numbers here, you can see that the polarity arrow that I have drawn points toward the bigger number. In other words, that's where the electrons want to go, is they are attracted to the element that is more electronegative. Now, if that's the case, and the electrons are pulled all the way to that side, then the end result is that the bond just breaks, and the H plus pops off, and it's now in the solution, and we have an acid. Now, electronegativity is not the only condition here. This is the most prevalent condition for this situation. Now, as a result of the bonds being very polar, the bonds tend to get weaker. But there's also another issue that comes up where you don't have electronegativity differences, but you end up having size differences. And this is what happens with things like HCl, HBr, and HI. As the molecules get bigger, so HBr, HI over here, so these are really big. The hydrogen has a harder time interacting with it. And what that means is that with hydrogen being so tiny relative to, say, iodine, there's very little overlap between the orbitals, relatively speaking, and thus the end result is that their bond that is formed is not as strong as it could be. Now, HF actually has a remarkably strong bond. And the reason for that, despite them being very, very, very different in electronegativity, fluorine versus hydrogen, the atoms are virtually the same shape and size, and so their orbitals overlap extremely well. And the consequence of that is that HF ends up being a weak acid. HF is kind of strange. We would actually predict HF to be, based on electronegativity alone, a really strong acid. But it turns out that it's weak, and it's because the molecule has atoms that are roughly the same size. They're all in periods 1 and 2. Same thing for H2O here. H2O not as electronegative as fluorine, so it is a weaker acid than fluorine. Also, it's the same size, more or less, as hydrogen. The 1s orbital and the 2s orbitals and the 2p orbitals are not huge orders of magnitude different in size. So they overlap well, and they have very, very strong bonds. So, very weak acid for water. A little stronger HF. And then you get to the big atoms down at the bottom of the periodic table, and they become very acidic. The next thing that we're going to look at for acids is we're going to look at things that are called oxyacids. Oxyacids contain lots and lots of oxygens, hence the name. There's also an extra atom in them. This atom is Y. I've labeled it Y. And the reason I labeled it Y is so I can say, yo. No, it's just because that was the label in the textbook that I was writing this slide from. Now, depending on how electronegative Y is, and how many oxygens are bonded to Y, you're going to get a stronger or weaker acid as a result. Now, the example that we are going to use here is we're going to use chlorates. So, we said earlier that perchloric acid is a strong acid. And we're going to justify that in the following way. Well, the Cl is electronegative, and it's got 4 O's bonded to it. So we've got lots of oxygens, and chlorine is pretty electronegative. So that's going to make for a very strong acid. Now, we would predict that HClO3 would be a weaker acid than perchloric acid. And the reason for that is, well, it's still got the same chlorine, but there's only 3 oxygens here. What do the oxygens do as a whole? Well, what they're trying to do is they're trying to pull the electrons towards themselves, because oxygen is the most electronegative atom in this molecule. Those O's are going to pull electrons from any source that they can, and one of those sources is going to be the bond between the H and whichever OH this is bonded to. So let's look at that on the next slide here. We'll come back to that one. This is the one I'm talking about right now. So here's my OH bond, and all of these oxygens are going to pull electrons in this direction. And as a result, the indicated bond is going to get broken pretty quickly. In fact, extremely quickly. It's a strong acid. But the fewer oxygens that are there, the less able these oxygens are able to pull electron density towards themselves. And as a result, with fewer oxygens, so here I have 3, here I only have 2, and then here I only have this 1, the Ka goes down. Interestingly, if you were wondering, is there an acid out there that has a Ka of 1? Yeah, it's this one. Chloric acid. Ka 1. If you have a 2 molar solution of it, exactly half of it will dissociate. So that accounts for how many O's are on there. Less O's means can't pull the electrons away from that OH bond as effectively, which means less likely to break if there are fewer O's. Let's go back to this slide real quick. Here I have different electronegative atoms in my bonds here. And what we observe is that the more electronegative the atom is, the bigger its Ka. And the reason for this is chlorine is going to help oxygen pull the electrons towards their end to try and break this bond, but bromine's not going to pull as much, and iodine's not going to pull as much either. So those are our 2 features in action for oxyacids. So if I ask you on the exam next week, hint, or on the quiz, which of these is a stronger acid, justify your answer. And I give you a bunch of like bromates. So I say BrO4 minus, BrO3 minus, etc. And I put H's on them. So I'd be like bromic acid, perbromic acid, etc. Without looking up Ka's, you should be able to answer that. And you should be able to tell me why. All right. On the screen here, I have formic acid and methanol. Based on the picture, which of these, A or B, is the stronger acid? So give you a minute to think about it, which really, I guess, is just two of the 3 people that are here in the lecture. So you can type in your answer, A or B, and we'll reveal the answer in just a second. All right, so let's check our 2 quick conditions. The first condition was which atoms are more electronegative. Well, the central atom is C, so that's not going to apply. Then we check for how many oxygens are available, and you're exactly right. Hey, I got 2 right here. 1, 2. But here I only have 1, so I'm going to have twice the pull away. So this should be the stronger acid. And it turns out that that's totally right, Formic acid is acidic, and methanol, it turns out, is not acidic at all. Now, interestingly, if you exercise, which you should, I personally don't, because I'm old and decrepit, but formic acid is what your body makes, which is the feeling, I believe, anyway. This is what you feel when, like, you get muscle fatigue. So, like, when you're running and you, like, feel the burn, it's formic acid. That's my understanding. Also, formic acid is something made by ants. I'm more confident in that one for some reason. I don't know. Oh, look, we made it through a section. Thank Thor. Okay, great. Okay, so that's everything that I care about for acids and bases and calculating their pH. We're going to keep calculating pHs and stuff in this section, but now what we're going to do is we're going to move to other things that are not just weak acid or weak base. We're going to start making salts, and then what we're going to do is find the pH of a salt solution. Salt solutions are just conjugates of acids and bases, so more or less it's going to be the same thing, except we have to do the Ka, Kb, Kw thing. Then we're going to go into polyprotic acids, which is just, oh, okay, I have a bunch of H pluses. What do I do? And it's basically the mixtures thing again. And then probably after the exam, I wish we could do buffers before the exam, but I don't think we're going to have time. Buffers is probably the most biologically relevant part of this chapter. So that's just an overview of where we're going. So let's talk a little bit about salts today, because I have what, 20 more minutes left? Yeah, we could probably get to some more calculations here. So if you have a salt, and the salt is soluble, so very important, it's got to be soluble. If it just sits there at the bottom as a solid, it's not going to show up in the equilibrium expression, and we don't care about it. If it's insoluble, we'll get to that in chapter 15. Any soluble salt will dissociate into a cation and an anion. And if those cations or anions are weak acids or bases, we get interesting features. Particularly, the pH of the solution would be affected. So we're going to look at examples that do that. So here's our first example. We got sodium bicarbonate. Sodium does nothing. And we'll talk about why in a second. But bicarbonate is a weak base. And so if I dropped sodium bicarbonate into water and then tested its pH, it would show up as basic. Very weakly basic, it turns out. Let me get my marks out of the way here. So we're going to concern ourselves with what do these things do? Now, it's going to be kind of difficult for you to predict just by looking at it. So I'm looking at this and I immediately go base. But you might be looking at that and going, either? And in reality, I can't really criticize you for that because, sure, I could add the H plus back on there and get this. Or I could just completely take it away, right? Either of those should work. So how do I know that it's a base? Well, the answer is I've taught this class for 10 years. That's really the reason. So we need a better way. We can't just do this for 10 years and then come back and take the exam, right? So, like, you can't send a copy of yourself forward in time to study all the possible conjugates. That's ridiculous. So what we're going to do is we're going to just look at conjugates. What is the conjugate acid versus the conjugate base? So if I have an anion, I'm going to look at that anion and say, okay, this could be an acid by adding H plus to it. And then I'm going to look at the strength of my conjugate acid. And based on that, I can then make a consideration. Is my salt going to be an acid or a base? So on the screen here, I've got chloride, fluoride, nitrate, and acetate. And I've got all their conjugates, hydrochloric acid, hydrofluoric acid, nitric acid, and acetic acid. Some of these are strong acids, and some of these are weak acids. And we're going to label them like this. So here are my weak acids. The conjugate of a weak acid is a weak base. So we're just going to link these like this. Now, we have other conjugates here. So here we've got these two. These are strong acids. And the conjugate of a strong acid is neutral. Oh, I even got the color right. Look at that. I don't read my slides beforehand. I know other instructors probably have like notes and stuff. I do this all from my brain, so when I match stuff up like that, I'm always impressed, and nobody should give a fuck about that. Like this is my ADHD brain in action. So is there a space in the word in action? It's up to, we'll leave that as an exercise to the viewer. So there you go. Weak acids conjugate is weak base. Strong acids conjugate is neutral. And so what you're going to do is you're going to look at the anion part of a salt and say, oh, okay, is the conjugate of this strong or weak? And that's going to tell you more or less what should happen to the pH in the solution. So let's do an example of that. If I take sodium chloride, so table salt, and I dissolve it in water, is the solution acidic, basic, or neutral? So let's split this into its parts. And then we're going to look at conjugates. I need a better color. This is too faint. So what we do here is the following procedure. But the conjugate of Cl- is HCl. This is a strong acid, which means that Cl is neutral. Now, we haven't talked about sodium yet. Sodium is actually the conjugate of this in terms of being a base, which makes it neutral too. If you have any cation by itself, that is just like a metal ion. So anything in group 1A or group 2A, it is the conjugate of a strong base, sodium hydroxide. Now, not really a conjugate because it doesn't differ by H+, but for the purposes of this, since you can't stick an H on there, you can't stick an H+ on Na+, it doesn't work, right? That's just what we will treat it as. All right. So we would predict that NaCl, since both of the components are neutral, that we generate neutral. And so that's what we get. All right. How about this one? Is sodium fluoride acidic, basic, or neutral? Well, let's split it into its pieces again. So again, sodium, we don't really give a shit about sodium. But fluoride here, the conjugate of fluoride is HF. And HF is a weak acid. Therefore, fluoride must be a weak base. And so our solution containing a weak base would be basic. So this is the thought process that you want to go to. Split it into conjugate. I've already screwed that up. Sorry. 1, split it into ions. 2, look at the conjugates. 3, based on the conjugates, tell me what the ions are and how they'll affect the solution. All right, so I'm going to give you a bunch of salts here. Oh, no, I'm not. I'm going to give you this table. This table just arranges the salts based on their strength. Now, we've talked about bases here because we're just talking about anions on our salts. In a little bit, we're going to talk about cations, which are going to mostly just be like sodium, not sodium salts, but ammonium salts of various degrees. But also, we're going to add in things like iron and aluminum, which are actually acidic. Huh? And we'll talk about that in chapter 15 a little bit. Maybe at the end of chapter 14. I don't know if... Wherever Lewis acids show up. Do we have Lewis acids in here? I'm just looking. Oh, it's right there. Yeah. So in like 5 slides, actually. Now, some anions are actually acidic. So, for example, the one I'm looking at is primarily right here. So, ooh, that's... Thanks, PowerPoint. You're the worst. So, hydrogen sulfate is quite acidic because H2SO4 is a strong acid, and the second dissociation is actually remarkably acidic. So if I had a solution of, say, NaHSO4, this would actually be acidic. And so this rule is not perfect, because from this we would have predicted, oh, wait a second, hold on. If I do this, well, the conjugate is sulfuric acid, and that's strong. But it turns out that this is just a weak acid. And the reason for this is because it's polyprotic, okay? So if we have multiple H's in here, this idea doesn't work super well. But if there's only one H, it does. And so you're going to notice that all the examples I gave you, there's only one H on their conjugate, so that'll be fine. So what I want you to do is tell me which of these is acidic, which one of these is basic, and which one of these is neutral. I'll give you a hint. None of them are acidic because we don't have any basic anions yet. So basic or pH neutral. I will number them for you. Go ahead and tell me what your answers are in the chat. We'll go over the answers in about 2 or 3 minutes. And then I guess we're done for the day because we're out of time. All right, let's go over the answers here. So I'm going to run out of time if I don't. So sodium nitrate. So don't care about the sodium part. There's our ion. What's the conjugate? That would have been nitric acid, which is strong. So therefore, this acid is neutral. All right, so there's the first one. For KNO2, I'm going to just squeeze this down here. Again, don't care about the cation here. The conjugate of this is nitrous acid, and that's a weak acid. So therefore, oops, I got to write this down. Therefore, this is a weak base. And so this would be basic. And then for number 3, more or less the same thing as number 2 here, right? So we've got our calcium hydroxide, or not hydroxide, sorry. Calcium acetate. Oh, why did I put that there? There we go. So calcium, don't care. There's our ion. Its conjugate is acetic acid, which is a weak acid. That means that this must be a weak base. And so this must be basic. There you go. We're going to show some more examples of these next week in lecture on Monday, when we go over some ammonium-containing ions, and more examples are forthcoming. So, there you go. All right, that is all that we have time for today, because I don't think I can do the next topic in... yeah, we're not going to do any calculations for pH in 3 minutes, so goodbye. We're going to get rid of that. All right, so important reminders. Make sure that you turn in lab worksheet number 2 this week. And then, probably most important, do not go to lab on Friday this week. If you do, the door will never open, and you will be left wondering, where is Wes? What happened? We'll never see him again. Oh, wait, no, lab is canceled because the NMR broke a second time, just after we fixed it. Thankfully, I'm not paying for it, so... All right, thanks for watching. Thanks for coming out to the lecture. Make sure you're doing the studying on this stuff, because we have an exam next week. See you on Monday. Take care.